Something happened 7 minutes ago that most people on this planet will never hear about. Not because it was hidden, not because anyone decided to keep it secret, but because the world moves fast, and the universe moves faster, and the gap between those two speeds is where the most important things in human history tend to disappear without a trace. A spacecraft 15 billion miles from Earth just did something it has never done before. Something it was never designed to do. Something that, according to the engineers who built it and the scientists who have spent decades studying it, should not have been physically possible given what it is, where it is, and how little power it has left to do anything at all. Voyager 1 turned around. Not literally, not in the way you were picturing. The laws of physics in interstellar space do not offer that kind of mercy. But its instruments, its sensors, the aging electronic eyes and ears that have been pointed outward into the darkness for nearly 5 decades, they received something coming from behind. From the direction of home, from a region of space they have already passed through and left behind. And what they detected in that direction, from a place that our models say should be quiet, should be settled, should be scientifically unremarkable, is something that nobody predicted, nobody modeled, and nobody can currently explain. This is not a malfunction. This is not instrument noise. This is not the kind of anomaly that gets quietly filed away and forgotten. What Voyager 1 has just detected, coming from the inner boundary of the Helios heath, the turbulent outer shell of our solar system that it crossed years ago and left behind, is a structured, directional plasma signal of a character that does not match any emission previously recorded by any instrument anywhere in the history of space exploration. And the implications of that sentence, if you follow them to their logical end, will change the way you think about where you live. Let us start with what we knew before this happened. Because context is not optional here. Context is everything. When Voyager 1 crossed the heliopause in 2012 and entered true interstellar space, scientists celebrated, and then they got to work. They had a set of expectations, a carefully constructed theoretical picture of what the region beyond the solar system should look like based on decades of remote observation, simulation, and inference. The interstellar medium was supposed to be sparse, cold in the electromagnetic sense, and relatively uniform. The heliosphere behind it, the vast bubble of solar wind that Voyager 1 had just exited, was supposed to be a closed system, a sealed environment. Something that, once left behind, would recede into the background and stop being relevant to the instruments pointed outward. What Voyager 1 found instead was a persistent narrowband plasma emission humming through the interstellar medium that no model had predicted. Scientists, after years of analysis, concluded that the interstellar medium is not quiet. It is turbulent. It has structure at every scale. It has what some researchers have taken to calling a personality, a physical complexity that makes the void between stars something far more dynamic and interactive than our textbooks ever suggested. That was already extraordinary. That was already enough to fill a decade of research papers and reshape the foundational models of heliospheric physics. But science, like Voyager itself, does not stop when you expect it to, because now the signal is coming from the wrong direction. Here is what that actually means, stated as precisely as the data currently allows. Voyager 1's plasma wave science instrument, the same system that has been detecting those persistent interstellar plasma oscillations since 2017, began registering an anomalous directional component in the emission pattern, not a new emission layered on top of the existing background, not a separate signal from some unknown external source, a structured perturbation within the ongoing plasma wave data that carries a directional signature pointing back toward the Helios heath, toward the inner boundary of the region Voyager 1 left behind more than a decade ago. The Helios sheath is the zone between the termination shock, where solar wind slows abruptly from supersonic to subsonic speeds, and the heliopause itself. It is roughly 25 to 30 astronomical units thick. A churning, chaotic region where solar wind piles up like water behind a dam, compressed and heated and redirected by the pressure of the interstellar medium pushing back against it. Voyager 1 spent years traveling through it. Every instrument on board recorded what it found there. And then it crossed the heliopause and left the heliosheath behind. Except the heliosheath apparently did not leave Voyager 1 behind. What the data suggests, and what researchers at JPL and collaborating institutions are currently working to characterize and verify, is that something in the heliosheath is generating an outward propagating plasma wave that has followed Voyager 1 into interstellar space. Not a random burst. Not a one-time event triggered by a solar flare or a coronal mass ejection, though those events have previously been used to calibrate Voyager's plasma density measurements. This is structured. This is sustained. This is behaving like a transmission, not like noise. And the universe does not transmit without a source. So, what is the source? Here is where the science gets genuinely uncomfortable, in the best possible way. Because there are currently 3 competing hypotheses, and all 3 of them are deeply significant, and none of them can yet be ruled out, and each one, if confirmed, would rewrite a different chapter of physics. The first hypothesis is that the heliosheath is experiencing a large-scale magnetohydrodynamic wave event driven by an unusual period of solar activity. The Sun goes through 11-year cycles of high and low activity, measured primarily by sunspot counts and the frequency of solar flares and coronal mass ejections. We are currently near the peak of solar cycle 25, and the activity levels have been higher than the models for this cycle predicted. If a particularly powerful sequence of solar events compressed the inner heliosphere with enough force, it could generate a magnetohydrodynamic wave, a disturbance in the plasma and magnetic field structure of the heliosheath, powerful enough to propagate outward and eventually reach Voyager 1's position in interstellar space, where the plasma wave instrument would detect its leading edge as an anomalous directional signal. If that is what this is, it means the heliosphere is a far more acoustically active system than we realized. It means that solar events do not just ripple outward through the solar wind and dissipate at the termination shock. They can generate structured wave phenomena that penetrate the heliopause, cross into interstellar space, and travel for distances measured in billions of miles while retaining enough coherence to carry a directional signature. That alone would be a major discovery. That alone would force a complete revision of how we model the relationship between solar activity and the structure of the heliosphere. The second hypothesis is more unsettling. It involves the heliopause itself. Scientists have known since Voyager 1 crossed it in 2012 that the heliopause is not the clean, stable boundary they expected. It is turbulent. It is in motion. It is subject to pressure fluctuations from both sides, solar wind pushing outward and interstellar plasma pushing inward, and the balance between those 2 pressures is not constant. It shifts. It breathes. There is evidence from Voyager's own data that the heliopause has a kind of wave-like instability along its surface, similar in mathematical character to the Kelvin-Helmholtz instability that causes turbulent rolling waves at the boundary between 2 fluids moving at different speeds, the same instability that creates those rippling waves you see at the interface of fast and slow layers in a river. If the heliopause is undergoing a significant Kelvin-Helmholtz event, driven by a sustained period of elevated solar wind pressure on one side and anomalous interstellar medium turbulence on the other, the disturbance could generate plasma waves that propagate both inward and outward from the boundary simultaneously. Voyager 1, now positioned well beyond the heliopause, would detect the outward propagating component as an anomalous signal coming from behind it, from the direction of the boundary it crossed, from what looks, to its instruments, like home. That hypothesis, if confirmed, would mean that the heliosphere is not behaving as a stable, self-contained system. It would mean the boundary of our solar system is in a state of dynamic instability, driven by forces on both sides of it, and that this instability has physical consequences that extend deep into interstellar space in one direction and potentially deep into the inner solar system in the other. It would mean the shield that protects every living thing on Earth from galactic cosmic radiation is not a fixed wall. It is a moving, breathing, dynamic surface that responds to the universe around it in ways we do not fully understand and have not yet learned to predict. Read that carefully, because that is not a theoretical concern. That is a statement about a physical system that directly governs the radiation environment in which all complex life on this planet has evolved. The third hypothesis is the one that the scientific community is most reluctant to discuss publicly, not because it is irresponsible, but because it is the most structurally radical, and science moves carefully when the implications are this large. It is the possibility that what Voyager 1 is detecting is not a wave propagating outward from our solar system at all. It is the possibility that there is a structure in the local interstellar medium, a large-scale magnetic or plasma feature external to our solar system entirely, whose leading edge Voyager 1 has just entered, and whose geometry, when mapped against Voyager's trajectory, produces a signal that appears to come from the direction of the Helios heath because that is the direction from which the structure's wavefront is approaching. In simpler terms, something is out there, something large, something structured, something close enough, in cosmic terms, to be interacting with Voyager 1 right now, in 2026, and that interaction is being registered by a 49-year-old plasma wave instrument as a signal that looks like it is coming from behind the spacecraft, but may in fact be coming from something in front of it that is simply so vast that its geometry wraps around Voyager's position in a way that confounds directional measurement. There are known candidates for this kind of large-scale interstellar structure. The local interstellar cloud, the diffuse region of warm plasma through which our solar system is currently traveling, has a boundary that some models place relatively close to the heliopause. Some researchers have proposed that the solar system may be in the process of exiting the local interstellar cloud entirely, a transition that would expose the heliosphere to a dramatically different external plasma environment and could generate exactly the kind of boundary interactions that Voyager 1's data is beginning to suggest. If our solar system is crossing a boundary in the interstellar medium right now, not in 1,000 years, not in 1,000,000 years right now, in the early 21st century, the timing is almost too extraordinary to absorb. The one moment in human history when we happen to have an instrument in interstellar space is the moment when interstellar space is doing something unexpected. Either we are extraordinarily lucky, or the discovery was always waiting for the instrument, and the instrument simply had to be there long enough for the universe to show itself. And now consider what it took to keep that instrument alive long enough to be here for this. In 2023, Voyager 1 went silent in a way that felt final. Not completely silent. The carrier signal was still present, but the data was incoherent, scrambled, a stream of corrupted information that the engineers at JPL could receive but not read. The cause was a single failed memory chip in the flight data system, a fragment of 1970s hardware no larger than a fingernail that had spent 46 years absorbing cosmic radiation in interstellar space and had finally reached its limit. One chip, one point of failure in a machine 15 billion miles away with no repair crew, no spare parts, and a communication delay of 22 hours each way. The engineers did not give up. They could not give up, because they understood, even then, that whatever Voyager 1 might still have to say about the universe was irreplaceable. There is no second spacecraft in interstellar space. There is no backup instrument. There is only this one machine, and everything it might still be capable of discovering before its power finally runs out. They spent months working through the problem in slow motion, each diagnostic step separated from its response by 2 days of waiting. They mapped the damage. They rerouted the software. They divided the corrupted code into fragments and redistributed those fragments across undamaged sections of memory in a machine they could not touch, using programming languages that predate the personal computer, across a distance so vast that the signal carrying their instructions traveled for nearly a full day before it arrived. And it worked. Voyager 1 came back. And now, in 2026, it is detecting something that justifies every one of those months of painstaking, agonizing, extraordinary work. The power situation remains critical. The radioisotope thermoelectric generators that power Voyager 1 are producing approximately 250 watts, down from 470 watts at launch, losing roughly 4 watts per year. The LECP instrument was shut down earlier in 2026 to conserve what remains. The engineering team is currently testing a power redistribution procedure on Voyager 2, informally called the Big Bang, designed to squeeze additional operational life from the spacecraft's electrical system. If those tests succeed, the same procedure may be attempted on Voyager 1 as early as mid-2026, with the possibility of briefly restoring power to the LECP and expanding the dataset on the anomalous directional signal. The window is narrow. It is getting narrower every day, and what is on the other side of that window, the data that Voyager 1 might still transmit before the silence comes, may be some of the most consequential information ever gathered by a human-made instrument. Because here is what all of this converges on. Stated without softening, without hedging, without the careful diplomatic language that scientific papers require. If any of the 3 hypotheses currently being explored to explain Voyager 1's anomalous directional signal turns out to be correct, the model of the solar system that humanity has operated on for the last century is incomplete in a fundamental way. The heliosphere is not a sealed, passive bubble. It is an active, dynamic participant in a galactic environment that is itself in motion, in flux, in a state of structured complexity that we are only now beginning to be able to measure. And the implications of that, for our understanding of cosmic radiation exposure, for the long-term stability of the conditions that support life on Earth, for every future mission to deep space, are not small. They are not incremental. They are the kind of implications that get written about in the history of science next to heliocentrism and quantum mechanics and the discovery of the cosmic microwave background. On November 18, 2026, Voyager 1 will be exactly 1 light day from Earth, 16.1 billion miles. A signal traveling at the speed of light will take 24 full hours just to reach it. The communication delay will soon be measured not in hours but in days, and then, sometime in the early 2030s, the power will drop below the minimum threshold required to operate any instrument at all, and the transmission will stop. Not because Voyager 1 will stop moving. It will never stop moving. It will continue at 38,000 miles per hour into a darkness that has no end, carrying its golden record, carrying the voices of every human language, carrying the sounds of ocean waves and human laughter into a silence so complete that no human ear will ever hear them arrive anywhere. But the data will stop. The map will stop being drawn. The one window humanity has ever had into interstellar space will close. And what we do in the time between now and that moment, how carefully we listen, how seriously we take what this dying machine is still trying to tell us, whether we find the will and the resources to build something to follow it before the gap in our knowledge becomes a generation wide, that is not a scientific question. It is not an engineering question. It is a question about whether we are a species that deserves the discoveries it stumbles into. Voyager. One turned around. It looked back from the edge of everything we have ever known and found something coming toward us from a direction we thought we understood. Something structured. Something unexplained. Something that the universe has apparently been waiting until now to show us. And the only instrument capable of showing it to us has less power than the light bulb above your head, is held together by the refusal of a small group of human beings to let it die, and is sending its findings home at the speed of light across a distance so vast that the signal you are hearing right now left that spacecraft before yesterday ended. The universe is not waiting for us to be ready. It never has been. It is out there right now, doing things we have no category for, generating signals we cannot explain, revealing structures that our best models never predicted, and it is doing all of this whether we are paying attention or not. Voyager 1 is paying attention on our behalf. It has been paying attention for 49 years. And in the time it has left, it may be about to tell us something so fundamental about where we live and what surrounds us that the world we understand today will look as incomplete as the world that ended the day Copernicus published. The signal is still coming. Faint, ancient by the time it arrives, stretched across 15 billion miles of void and cold and magnetic complexity that we are only beginning to understand. But it is coming, right now, this second. A machine the size of a small car, older than most of the people watching this, is whispering to us from the edge of everything. The only question worth asking, the only question that has ever really mattered in the entire history of human curiosity, is this: are you listening? Because this is the moment, not a future moment, not a moment that will come when the funding is better, or the technology is ready, or the timing is more convenient. This moment, right now, with one spacecraft and a narrowing window and a signal we cannot yet explain, is the moment when the universe chose to speak. What you do with that, whether you share this, whether you think about it, whether you demand that the people who make decisions about what humanity pays attention to actually pay attention to this, is not a small thing. It is not a gesture. It is a choice about what kind of civilization we intend to be when the last signal finally fades and the darkness takes back everything it loaned us.